Welcome to follow presentation about the Lithosphere-Asthenosphere boundary. This presentation consists from two parts. Part 1 presents a review of different definitions of the lithosphere and the LAB proxies. We will show different definitions and methods based on measuring different physical parameters, vertical and lateral resolutions of the methods, as well as examples of LAB models. Part 2 focuses on LAB modeling as a transition between two layers or regions with different anisotropic fabrics. The lithosphere is the outer rigid shell of the Earth, which comprises slowly moving lithospheric plates with diversely defined lower boundary. The Lithosphere-Asthenosphere Boundary, LAB, is the first-order discontinuity in the Earth that accommodates differential motion within the tectonic plates, the lithosphere, and the underlying upper mantle, the asthenosphere. The LAB is the most extensive type of plate boundary on the Earth. Definition and modeling of the lower boundary of the plates is extremely important from the point of view of plate tectonics. However, detection of LAB remains elusive, especially beneath the cratons. Measuring different physical parameters and application of different methods result in different definitions of LAB, differences in LAB depth and their uncertainties, different lateral and vertical resolutions, or different sharpness of the boundary. There are various definitions of the lithosphere, among which belong the lithosphere as thermal boundary layer, seismic velocity boundary layer, electrically resistive outer layer, mechanical boundary layer, rheological, petrological, or elastic layers. Let's start first with lithosphere as a thermal boundary layer. The thermal definition presents the lithosphere as the thermal boundary layer of the Earth on the top of the convection system in the mantle. Thus, the lithosphere represents a surface layer where its geotherm deviates from adiabat in the mantle below and is considered to be a conductive lid of the Earth. In this case, the LAB is the thermal transition layer, a depth interval with a geotherm intermediate between the conductive and adiabatic geotherms. The base of thermal lithosphere is assumed approximately in the middle of the thermal transition layer. In seismology, the lithosphere is defined as seismic velocity boundary layer down to a velocity decrease in the upper mantle. Original definition of seismic lithosphere comes from Benno Gutenberg. It says that the lithosphere is the high-velocity outer layer of the Earth underlain by a low-velocity zone or a region where positive velocity gradient diminishes. According to this definition, the LAB lies at depths of a large and sharp velocity drop, or at least a depth where the positive velocity gradient weakens due to a change in material composition, presence of partial melt, change in seismic anisotropy, and others. This slide shows relationship between thermal and seismic lithosphere thickness. Z1 marks base of conductive thermal boundary layer. Z2 is base of thermal lithosphere, which corresponds to the intersection of the linear continuation of the conductive geotherm with the mantle adiabat, and Z3 denotes the top of convective mantle, marks total thickness of a layer with temperature contrast relative to surrounding mantle, and also the base of seismic lithosphere. Next definition describes the lithosphere as electrically resistive outer layer of the Earth. Then the LAB marks the transition zone between resistive lithosphere and increased conductivity in the asthenosphere. One should keep in mind that bulk conductivity in the mantle is primarily controlled by temperature and composition. Lithosphere definition as a mechanical boundary layer assumes the lithosphere composed of individual coherently translating plates. Base of the mechanical boundary layer is associated with zones of reduced viscosity in the upper mantle and asthenospheric flow. Mantle viscosity is strongly temperature dependent. Therefore, the thickness of the mechanical boundary layer and the mechanical LAB depth should be proportional to thickness of thermal boundary layer and thermal LAB. Mechanical LAB can be constrained from variations in texture of xenoliths brought to the surface from different depths in the mantle. One of modern definitions associates LAB with thermally induced, elastically accommodated grain boundary sliding, along with a jump in water content. This is valid for oceanic and presumably also for the continental LAB. Among lithosphere definitions belongs also that as rheological layer, the strong outer shell composed of the crust and the upper part of the mantle down to a depth where shear strength drops. Then the rheological LAB is a depth where the strength drops below a particle value, for example 1 megapascal. This definition is close to the mechanical one as above. Petrology defines the lithosphere as the crust and the melt-depleted part of the upper mantle, occupied dominantly by metasomatized mantle rocks. This is a kind of chemical definition of the lithosphere. Base of the petrological lithosphere is associated with change from depleted lithospheric to undepleted asthenospheric trace element signatures in garnet. Depth variation of mantle composition is sampled by mantle xenolith, which is widely used in studies of cratonic regions. Last example of the lithosphere definition describes it as elastic layer, mechanically strong outer shell of the Earth that supports applied load elastically and without permanent deformation. Viscoelastic rocks exhibit elastic behavior only under short duration of stress. Thus, the effective thickness of elastic lithosphere depends on time load and delineates the thinnest lithosphere among all the definitions. Measuring different physical parameters in the definitions of the lithosphere and LAB, applying different techniques, aim at retrieving fundamental characteristics of LAB, its depth, sharpness or width of the transition, magnitude of the change of the physical parameter across the boundary, and sensitivity to variations of LAB depth. Different LAB models retrieved from different methods and data agree mostly in gross features. The LAB is deepest beneath the Precambrian continental provinces, shallower beneath the Phanerozoic continental regions, and the shallowest beneath oceans. But it can differ substantially in individual subregions. In following slides, we will present examples of different models of the lithosphere thickness and LAB depth. The first example shows the LAB as the thermal transition layer, that is depth interval with geotherm intermediate between conductive and adiabatic regions. The LAB is associated with about 1300 degrees geotherm. It represents a relatively broad vertical transition zone with no sharp changes in temperature and with low lateral resolution. Moreover, depth profiles of internal heat flow and thermal conductivity are needed for calculation of geotherms at depth from surface heat flow data. The thickest lithosphere, the deepest LAB, is in cratonic regions in Northern America, Brazil, Western and South Africa, Baltic Shield or Siberia. This slide shows LAB as a top-of layer with increased electrical conductivity from magnetotelluric measurements. LAB in Phanerozoic Europe, west of Trans-European suture zone, is shallower on average than LAB in the Precambrian Europe. LAB at approximately 250 kilometers or more is in Fennoscandia and Eastern European Craton, but also beneath the Western Bohemian Massif, which is incompatible with other methods, imaging there the shallow to normal depth continental LAB. In the Pannonian Basin or in Northern Apennines, the LAB updomes up to about 60 kilometers. This map compares LAB depth from magnetotelluric measurements with seismic LAB in Central Europe. The LAB depth marked by isolines is defined according to the original definition as the bottom of the high-velocity outer layer of the Earth. Numbers ascribed to the squares mark the electrical LAB. We see here the good agreement in the Pannonian Basin, Rhenish Massif, Southern Rhine Graben, and also in the western rim of the Bohemian Massif. Fair agreement is in the main part of the Bohemian Massif and the Carpathians. Sparse electromagnetic results over the Alps at the time did not show satisfactory agreement at all. Magnetotelluric signal is measured prevailingly on continents. However, satellites detect tidal magnetic signals from which electrical structure of the oceanic lithosphere and upper mantle can be imaged down to a depth of about 250 kilometers. Here we show models of electrical conductivity and their comparisons with mineral physics constraints. On the left, the retrieved conductivity lies between values for the dry and wet olivine, the main constituent of the upper mantle material. On the right, we see a comparison of the model from satellite data with local conductivity models derived from seafloor magnetotelluric data in Philippine and Pacific regions. The results correlate well with the average seismic oceanic LAB. Presence of a low-velocity zone beneath the high-velocity lid or its absence is taken as an indication of LAB seismic velocity profiles. Different types of seismic waves propagate through the Earth, and independence on their wavelength, direction of propagation, velocity, polarization, conversion, attenuation, and etc., they sample depth structure of the Earth. Surface wave models of absolute shear velocities (VSV) are primarily used to model global LAB on the Earth. However, when inverting surface wave dispersion, it is impossible to distinguish the sharp velocity contrast across the LAB from a gradual velocity gradient. The lithosphere thickness can be derived from models of absolute shear velocity as the depth range of the strongest positive velocity gradient. The LAB is often associated with a depth of 1 to 2% positive anomaly above a global reference Earth model of shear velocity, or with a depth of the center of the negative gradient. Uncertainty of the LAB depth is several tens of kilometers, even in case of a strong negative velocity gradient beneath the high velocity lithosphere. These are LAB models from shear velocities of surface waves both beneath the continents, upper figure, and oceans, figures in the bottom. Beneath the continents, the LAB is set as 2% positive velocity anomaly relative to IASP-1 radial velocity model. Similarly to the thermal model, we see the deepest LAB beneath the Precambrian provinces. Beneath oceans, the LAB is derived from shear velocity as the depth of maximum negative velocity gradient in the Pacific, Atlantic, and Indian Oceans. The lithosphere is thin along the ridges and thickens with its age. Another possibility to determine LAB beneath oceans is based on changes of radial anisotropy, the upper wall. The LAB depth is set as the depth of maximum of the positive gradient of radial anisotropy. For comparison, the bottom row of figures shows the LAB depth from the gradient of the shear velocity as on the previous slide. Figures are plotted on the same scale. We can see significant differences in the LAB depth. LAB from radial anisotropy is still lower than that from the VSV velocity. Moreover, in case of LAB determined from radial anisotropy, the age dependence is limited to very young ocean regions. This slide shows the LAB in the Pacific Ocean as the top of the correlated layer between the plate motion and the fast axis of the azimuthal anisotropy. If we compared it with previous models, then the LAB from different parameters differ both in depth and in depth variations with age of the lithosphere. In large-scale body wave tomography, the thick lithosphere appears as regions with positive velocity perturbation, that is, regions with velocities higher than that of the reference radial model of the Earth. The model gives more realistic LAB estimates for the Alps and Northern Apennines in comparison with electric LAB or LAB from surface wave velocities. Smooth variations detect gross features of LAB, but no sharp changes or small size local phenomena, for example, plume-related lithosphere thinning. Such features can be retrieved in regional teleseismic P-wave tomography, which revealed, for example, 3 differently thick domains of the lithosphere in the French Massif Central, or significant lithosphere thinning along the southwest-northeast trending Eger Rift in the western Bohemian Massif. This slide shows LAB model derived entirely from shear body wave tomography. Similarly to models from surface waves, the lithospheric base is defined as the depth where Vs velocity in the upper mantle is 2% higher in comparison with the global continental velocity model IASP-91. Next slide shows a comparison of this model on the left with model from surface waves on the right. The gross features, thick lithosphere beneath cratons, dark blue regions, are similar in both models. The LAB from body wave tomography has higher lateral resolution and maps distinct lateral variations of LAB depth. But there are regional differences between the two models. For example, regions in southern and western South America, eastern Greenland, Tibet, and others. Next slide compares the LAB from shear body waves, lower figure, with the thermal model, upper figure. Similarly to the surface wave model, the thermal model is smoother than that from body waves. The comparison on the right side shows that seismic LAB beneath Precambrian regions, cratons, is deeper. Expansion of computer facilities enables complex and time-consuming calculations of full waveform inversion, which incorporates both the body and surface waves. This slide shows cross-sections through the models in Eastern Asia. The thick lithosphere and deep LAB appears as the blue high shear velocity perturbations in Tibet, whereas thin lithosphere and cylindrical low velocity anomaly is modeled beneath the southern tip of the Baikal Rift. Next slide shows 4 cross-sections through full wave inversion in Japan region. Profiles across Honshu and Izubonin shows down to 660 discontinuity westward and southwestward dipping thin Pacific plate along with earthquake foci. Cross-sections beneath the Ryukyu image shallower subduction of the Philippine plate. Receiver functions represent a relatively new technique of modeling discontinuities in the Earth. In reality, the discontinuities are narrow zones where velocity changes from velocity in the region above and that beneath it. The zones must be sufficiently narrow relative to wavelengths and separate regions with relatively large velocity changes. If the contrast is sharp enough, the incoming waves reflect, refract, and convert from one type to the other and interfere when propagating further to the receiver. This results in P-wave coda or S-wave precursors. Along with MOHO, the LAB belongs to the Earth interfaces successfully mapped by the receiver functions. Let's concentrate first on interference of on-LAB reflected and refracted SS shear waves. This slide shows modeling the LAB depth from shear waves which reflect at LAB beneath the bounce point in the middle between the source and receiving stations. Incoming shear waves reflect both at the bottom of the LAB and at the surface, interfere, and create SS reverberations at stations. This method is based on forward modeling the SS waveform recorded at the receiver. Advantage of this method is that it allows mapping LAB depths at regions without seismic stations, for example oceans, as it is shown here for the Pacific region. Modeling discontinuities beneath a single station or array of stations utilizes conversion of body waves at the discontinuities beneath the receivers. In case of P to S conversions at LAB, The LAB signal arrives in one package with PS multiples due to the VP, VS and MOHO LAB depth ratios. Nevertheless, the receiver functions have good potential for quantifying the sharpness of lithosphere interfaces, particularly using the higher frequency signals available in P-waves. Depth to the interface derived from PS receiver functions lies at approximately 1785 km and correlates with tectonic environments. It is associated with LAB in the Phanerozoic regions, but it is too shallow in the Precambrian regions. Crustal reverberations in PS receiver functions can obscure the signal from the upper mantle interfaces. This is eliminated in SP receiver functions in which the SP peak precedes the S waves. There are various methods of migration of the delay precursor's times to depth. However, external velocity depth models are needed in any case. This slide shows example of LAB depths beneath Africa derived from S receiver functions. The south-north cross-section shows distinct variations of LAB depth, which reaches 300 km beneath the Precambrian shields in south and shallows up to approximately 70 km in the tectonically active Afar region in the north. Next slide shows LAB signal along with signal from other mantle interfaces on several profiles in Europe. These are SP receiver functions along the east-west profile between the Bohemian Massif and the Baltic Sea. The main SP peak is at relatively constant depths. The plot shows a newly identified tipping sublithospheric discontinuity SLD. The depth-migrated SP receiver functions on the south-north profiles in Central Europe image the distinct LAB in Phanerozoic Europe, weaker MLD in the Precambrian Europe, and there also deeper cratonic LAB-C. This slide compares the LAB image from SP receiver function with LAB from seismic tomography and MLD with the discontinuity derived from post-glacial rebound or from controlled source seismic experiments. There are two low velocity zones beneath the shield on top of each other. The SP receiver function is the broadly used method for mapping the LAB in seismology. However, for getting a clear LAB image, the method requires a large amount of shear wave recordings with good azimuthal coverage, which is not always fulfilled. Otherwise, smoothing over hundreds of kilometers limits the resolution of lateral variations of LAB. Contrary to thick lithosphere of the Baltic Shield, this slide shows shallow LAB in the Pannonian Basin, surrounded by the mountain ranges of Carpathians, the Alps and Dinarides. The lithosphere thins to about 50 kilometers in the central part of the Pannonian Basin. This slide shows how two different velocity models, EASP91 and EU60, used for depth migration of the receiver function can affect the LAB depth. In this comparison, the LAB relief with EU60 is smoother, LAB is deeper in Pannonian Basin and shallower in surrounding mountain ranges and the Bohemian Massif. Here we show a comparison of two seismic models which use the same reference model, IASP91, but the models are derived with different techniques. The LAB model on the left is from the SP receiver functions. The model on the right treats the lithosphere as the high-velocity outer layer. The LAB lies at about 50 kilometers depth in the central part in both models, but relief to the surrounding mountains is more distinct in the model on the right side. Comparison of LAB depth from SP receiver functions in Central Europe with the original seismic one shows that LAB from the receiver functions are systematically shallower, blue colors in the figure on the right, except of LAB in the northern part of Central Europe. LAB can be modeled also by joint inversion of PS and receiver function, as it is shown here for the Western Alps. Heat plots of the resulting VP and VS velocity depth distributions are shown for one station in the middle of the area, sitting on the model cross-sections in the lower left. We see that the European and Adriatic lithosphere have comparable thickness of 90 to 100 kilometers and collide below the Ivrea geophysical body. This might indicate that the European plate does not subduct continuously below Adria at present. The flat LAB discontinuity detected from SP receiver functions crosscuts the elongated high-velocity anomaly imaged in teleseismic tomography by Zhao et al. At about 90 km depth on the right, while is consistent with the depth distribution of velocity anomalies in other two models imaging a slab detachment at shallow depth. This slide shows variation of LAB in the oceanic continent transition in the area of Spitsbergen, Svalbard archipelago in the high Arctic, derived from a compilation of existing seismic, gravity, and thermal models. The 800 km long transect shows the shallowest LAB at 12 km beneath the ridge on the southwest. LAB depth increases to normal 300 km beneath the Atlantic Ocean. Seismic LAB attains 55 km beneath the Southern Spitsbergen, and thermal LAB is at 90 to 100 km beneath the continental structure of the Barents Sea. LAB updoming further to the northeast is related to the volcanic provinces. The LAB can be also imaged by seismic reflection techniques of control seismics. The presence of two continuous reflections covering approximately 300 million years interval of the old oceanic lithosphere were imaged in the Atlantic Ocean. The upper reflector, red, follows the 1250 degrees isotherm. The deeper reflector, green, lies at a constant depth of approximately 75 kilometers. The authors attribute the shallowing LAB of the older Atlantic lithosphere further to the east in the Guinea Bay to the lithosphere rejuvenation, possibly caused by volcanic islands St. Helena or Cameroon plume. The depth invariable reflector, green, follows the LAB depths derived from radial anisotropy of surface waves, while trend of the shallower interface, red, follows the thermal models. This slide shows a schematic model and interpretation of the LAB and G reflections as function of age of the oceanic plate. LAB follows the 1250 degrees isotherm for lithosphere ages larger than 12 million years. The deeper G discontinuity is interpreted as dihydration boundary formed at ridge axis, which separates the primitive mantle beneath from the depleted mantle above. Here we present global models of the LAB depth in the Earth, derived from different data and methods plotted on the same scale. We see LAB from SS precursors, upper left, as the 1300 degrees geotherm in the thermal model, LAB in effective elastic thickness model, and LAB based on global seismic tomography anomalies. The LAB is the shallower in the model of the effective elastic lithosphere thickness. In general, the models agree in the gross features. Rickert et al. Compared shear velocity profiles from surface waves and various LAB depths estimated for oceans and Phanerozoic and Precambrian continents derived by different techniques. Beneath oceans, the LAB deepens with age, and intervals of LAB depth from different methods broaden with age. A rough increase of LAB depth from the Phanerozoic to the oldest Proterozoic and Archean continental interiors can be seen in the heat flow, elastic and seismic models, but not a simple monotonic thickening with age as in the oceans. LAB depths from the receiver functions, blue dots, exhibit the largest variability. This slide compares continental thickness from seismology, SS modeling, and from diamond-bearing xenoliths PT data. The xenoliths suggest a chemical continental lithosphere at approximately 175 kilometers, whereas seismic tomography supports a much thicker route, more than 250 kilometers, and a gradual lithosphere-asthenosphere transition consistent with a thermal definition. This slide compares thermal thickness of the lithosphere based on shear velocities in different global tomography models. The LAB depth and relief differ even in models from the same physical parameter, shear velocity, VSV. Again, the gross features are similar, but they differ notably in lateral resolution. Here we present schematic interpretations of LAB properties for oceans, tectonically active continental provinces, and cratons, which are consistent with constraints from Rayleigh waves and converted and reflected body waves. In oceans, the LAB depth is consistent with thermal boundary at base of the cooling plate, but enhanced velocity gradient from partial melt is required. In tectonically active continents, the single thermal boundary is possible, with melt enhancement likely in some locations. Both in oceans and the active continents, the LAB is relatively narrow zone, shallower beneath oceans, deeper beneath the continents. Beneath the cratons, the oldest provinces, the LAB is the deepest. The transition zone itself broadens and the velocity gradient is debated. Moreover, additional intralithospheric discontinuity, MLD, about in the middle of the lithosphere is modeled in the cratonic regions. This slide summarizes LAB depths based on different definitions of temperature-dependent physical properties of mantle rocks. Bunch of LABs lie in interval of 0.85 of solidus temperature, where the mantle rheology changes, to solidus temperature T of the Earth's mantle material, which is the top of large-scale mantle convection. These are namely models defining the LAB as rheological, compositional, and chemical transition, specifically from seismic data as the top of low-velocity zone or changes in anisotropy, from electrical conductivity as the top of layer of increased conductivity, or from petrological data as changes in texture and bulk composition in mantle xenoliths. The deepest LAB comes from large-scale seismic tomography or mantle convection models. In literature, one can meet with terms perisphere or tectosphere, introduced by Jordan, as alternatives to classical concept of lithosphere and asthenosphere separated by LAB. This slide presents two models of the continental lithosphere. Model from geochemistry considers presence of zones of melts and fluids and formation of diamonds at the base of the lithosphere. Surface wave tomography model includes seismic anisotropy in the asthenosphere, which might enhance the lithosphere contrast across the LAB. Two layers are considered in the cratonic lithosphere above the anisotropic asthenosphere due to the flow of the mantle material. The upper lithosphere layer is considered as chemical layer and the lower as thermal lower layer, separated by MLD. There are also LAB models which consider anisotropy both in the lithosphere and the asthenosphere. In the last slide of this part, we show formation of anisotropy in the oceanic lithosphere and anisotropic fabric of domains of the continental lithosphere. The lithosphere is formed in mantle ridges and thickens when it cools and moves away. During this process, an isotropic pattern develops in the oceanic lithosphere with vertical low-velocity axis and subhorizontal high-velocity axis in direction of movement or mantle flow. The continental mantle lithosphere appears as a mosaic of rigid domains with own differently tilted fabrics. Such an isotropic pattern could develop during subduction processes, break-offs of the continents, wandering, and amalgamation of the fragments and formation of new plates. Petrological and chemical studies are confined to boundaries, sutures of lithospheric blocks, along which mantle material can be exhumed. On the other hand, seismic waves sample entire volume of the individual tectonic regions. Modeling the LAB as the boundary between the fossil anisotropy in the mantle lithosphere and present-day flow-related anisotropy in the asthenosphere, derived from anisotropic signals in the surface and body waves, is the subject of Part 2.